All right, let's start. Good morning. So this week we're going to transition to continuity. It's still, in my opinion, not calculus proper. For me, calculus are things like integrals and differentials or derivatives. And somehow continuity is, while related, it's a lot more malleable, let's say. It's a lot more plastic. But still, we have to start from it. I'm going to take attendance today, as usual. The procedure is standard. We have a couple things to discuss regarding sequences. I want to do a couple more examples. We had seen an example of a sequence converging to 0. Maybe we can come up with a couple of examples that do not converge or converge in a certain different sense. But like I said, so far we're just focusing on convergences of sequences of real numbers or extended real numbers, we're going to see also. And then we have a couple theorems regarding sequences, or rather their convergences. Then we're going to transition to continuity, but probably that's going to take at least one more class. So just to recap, we have, if you have a metric space X, now remember last week when I was using this notion of a metric space, I used X comma D. But in practice, what you would see is they would just call X to be a metric space with the idea that there's an intrinsic or implied metric. You're just not sort of being explicit about it. But this is a very common way of writing things. And if I have a sequence in X bullet, and X infinity, my target, then X bullet converges to X infinity if this happens. For any epsilon, for any error, I can find some finite time such that after this finite time, I am guaranteed that my terms in the sequence are within an epsilon of the target. But that's the standard definition. That's going to be the sort of general definition. Here are two exercises. These are like logical things. Because somehow, in certain circumstances, this epsilon being an arbitrary real number ends up being rather unwieldy. And so instead of looking at arbitrary epsilons, you can look at arbitrary k's, integers. And instead of epsilon, you can just focus on errors of the form 1 over k. This is logically equivalent. Another equivalent statement is instead of looking at errors of the form 1 over k, you can look at errors of the form 1 over 2 to the k. These are all equivalent statements. Given the situation, all of these sort of end up being useful. For instance, with this, there's also this information theoretical interpretation, namely that for each k, you have one more bit of information, in a sense. And you say, how much more do I need to wait to gain, to better my error margin, one more bit, for instance, or one more digit. So in computer science, for instance, this style is used a lot more. In any event, like I said, this is like logical, these two, logically equivalent to this. In the case of x equals r, now I have a sequence of numbers that converges to a sequence, to a point, to a number. If for any epsilon there's an n such that after this n, the absolute value of the difference between x sub n and x sub infinity is at most epsilon, right? Because this expression over here is nothing but the distance, the standard distance between the nth term and the target. And you would see this too typically, without sort of writing where epsilon is coming from. 99% of the time in this class, when people talk about epsilons, they really mean a positive real number. There are certain situations where epsilon is sort of like a negative number, or it could be like some number larger than 1, but that is sort of psychologically not the, or like sociologically, let's say, is not the most common thing. Epsilon you should think of as a positive number, and in principle it's a number much smaller than 1, 2. So you should think of epsilon to be something like this. It's a very small number, okay? Approximately. This should be your heuristic. And then finally, we have this situation. We would like to be able to make sense of a sequence of numbers converging or diverging to infinity. That we can make sense of in the case of x being the extended reals. Remember, so this was this set of extended real numbers. Extended reals. And the point was that in this set x, now we had this infinity as a point and minus infinity as another point. And so we would like to make sense of this expression. And so you say, oh, then your epsilon is going to be your error margin. Well, when you're talking about epsilon being the error margin to infinity, well, you're going to take arbitrarily large values, m, such that if you wait long enough, then your terms are going to be larger than this. And probably I should even get rid of this x sub n, this absolute value. It should be like this. Okay. This is, we can take it to be a definition as a special case of this. If this somewhat bothers you, this infinity, you can just take it to be an additional definition that is applicable only in the case of extended reals. And of course, you can also think about x bullet converging to minus infinity. But I'm going to leave that to you to write down. It's completely analogous. Exercise. Define x bullet converging to minus infinity analogously. OK. Any comments or questions about any of this so far? Like, I realize that these expressions take up quite a bit of time to get used to. Oh, maybe what we can do is we can also write down what these mean in simple English, because I think in the textbook they don't use these symbols. They use like standard English. But eventually this does start getting confusing. So let's write that as well. I can say, if and only, for instance, x sub n is arbitrarily close to x infinity for sufficiently large n. Close to x infinity for n sufficiently large. That's one way you would see it. Another phrase, perhaps, would be this. X bullet converges to x infinity if, for any epsilon positive, x sub n is within an epsilon of x infinity for all but finitely many n. For any epsilon, x sub n is within an epsilon of x infinity for all but finitely many n. So you need to discard some finitely many terms, and then after that, you're within an epsilon of the targets. For all but, I'll write it better, finitely many n. Often you'll see this phrase abbreviated as well, FABFM, for all but finitely many. FABFM. Okay. Any comments or questions about any of these? Okay. So let's switch back to examples. we had done this 1 over n example. Another example perhaps would be, say, y bullet. Let's be explicit. Let's say we started at 0. At time n, I want my term to be at -1 to the n. Okay. So this is an oscillating sequence. It's a periodic sequence if you want. If you want to draw the space-time diagram, this oscillates between +1 and -1. Okay. It's 1, then like so, and then like so. Okay. So this whole shape is x, or rather y bullet. If you want to only think of the space part, so the real part, what you would do is you would collapse this time dimension and just look at the vertical, in which case you would see this. Just as this is the real line, here is +1, here is -1, and your sequence just jumps between these two. Okay? Starts here, and then jumps here. Okay? Both of these are sort of ways to visualize. Okay? Now, let's do a poll. How many of you think this is convergent? How many of you think this is not convergent? Pretty much all of you. Very good. Why? Because, well, the point is that convergence should be about stabilization, but this guy never stabilizes at any given point. So we would like to say that this guy is divergent. Okay? It's clear, and it matches with your intuition, but we would like to be able to be formal about it also. So let's say claim y bullet is divergent. Now I should ask you, like, how could we perhaps argue for this claim?
We pick a small enough epsilon such that you can never, it's never in that range, even for sufficiently large n.
Exactly, right? So now, what is the definition of a sequence being divergent? It means it is not convergent, right? Here it is perhaps clear, but later on the statements are going to get more and more complicated, and that's where I think you're going to start enjoying or benefiting from these logical things. So let me try to use this logic stuff to try to figure out what I'm really trying to prove. Okay, so I'm going to write down the definition of what it means for y bullet to be convergent, but then I'm going to negate everything. Okay, as a logical operation. So this is my symbol for not. Now I'm going to write down the logical statement that corresponds to saying that y bullet is convergent. Now in this case, one perhaps complication here is that convergence is defined in terms of this, but here the target is determined. But a sequence is convergent if it converges to some point. So what I would really need here is to say there is a y infinity such that y bullet converges to y infinity. Just being fast forwarding all this. Okay. So what does this say? Within these brackets, there is some target such that for any epsilon, if I wait long enough, y sub n is going to be within an epsilon of y infinity. In other words, there is some y infinity such that y bullet converges to y infinity. That's what this statement within the brackets say. And here is the not operation, okay? Not blah, blah, blah. And how do you do this negation? In a sense, it's an algebraic operation, okay? You keep the order of everything. Exists turn into for alls turn into there exists, and the final statement you negate. So, for any y infinity, there is an epsilon such that for any capital N, there is a lowercase n after capital N, such that the distance between y sub n and y sub infinity is at least epsilon. This is the sort of algebraic way of negating a statement. Okay. So some of you might be much more comfortable with negating statements and stuff like that. I remember when I was first taking this class, I would have a hard time sort of negating what is being said. I would just write things down and sort of open them up using logic. But what is this saying? In simple English, this says, if I had a possible target y sub infinity, in fact, there is some error margin that misses infinitely many times. For any capital N, there is a lowercase n after capital N. Okay? And then later on, we're going to sort of make sense of these two things as well. You see, there's this part. There is an n such that after something happens, this is the for all but finitely many. For all but finitely many corresponds to this part. There is an n such that after that capital N, things happen. The opposite of it, in a sense, is for infinitely many. For any capital N, there is an n larger than it. After it, something happens. Okay, so this we're going to see later also. Any comments or questions about this? Yeah.
If a sequence doesn't have a value that it converges to, how can you find y infinity?
Well, that's the point. You cannot. What this is saying is that for any y infinity fails to be the limits of y bullets.
Right, but since there isn't one, then how do you use that to prove the statement?
I understand the point you're making. Let me try to explain. Maybe I should ask you, how else could I try proving this, if this is supposed to have a proof?
Maybe like there are candidates of y infinity.
Yeah, I'm saying, I'm being unbiased. I'm saying a candidate in principle is going to be ultimately a real number. I'm taking all possible candidates into account. If y bullet is supposed to converge, it is supposed to converge to a real number by definition. And I'm saying, let me consider all possible candidates. I take an arbitrary candidate, and then I realize through math that, in fact, that candidate is not going to work. None of the a priori candidates are going to work. No, I mean, I get the point. I get the point you're making. I would need to think a little bit more. I feel like I can come up with a better answer, perhaps. But Any other comments or questions for now?
About negating that logical statement.
Yes.
It looks like you flipped everything except the inequality between little n and big N.
Yeah, so
Why that?
because that inequality is not part of the sort of, so the inequality that you're flipping is this. Flipping this inequality would be to change, would correspond to changing the set.
What was that a subset of?
No, like, but I could have written this as for any n. This I could have written as for any n here. You don't touch the set. So your variables always come from the same place. So if I were explicit, I would say for any y infinity, there's an epsilon positive. I'm also not saying there's an epsilon negative, for instance, here. This epsilon is still positive. For any n, capital N, integer, positive, there is a lowercase n, integer, that is bounded from below by capital N. The only thing that you're negating is this open statement, they would say. So you don't touch the sort of where these variables are coming from. You keep those, you keep the sets, you only flip the quantifiers here. Everything else stayed the same, and then you flip this. Yeah. Like I said, like this is not absolutely necessary. If this feels a lot better, maybe you can try negating this as well. You could say there's an epsilon such that x sub n fails to be within an epsilon of any x sub infinity for all but finitely many n's. The problem with trying to negate things in English is, as far as I'm concerned, or at least in my experience, is that somehow negating things in simple English, they're like more murky. It ends up being somewhat more confusing to me. It's because you know, somehow negating things in English perhaps seem to be working differently. But when it comes to logic, it's an algebraic operation at the end of the day. It's an algebra. In fact, it's called Boolean algebra. Leibniz, in fact, was fascinated by this idea that even logic itself is a mathematical thing. So, mathematized. Anyway, so how to go about doing all this? Well, what I can say is this. Say y bullet converges to y infinity. Okay? In fact, I'm proving this, but proving this is the same thing as proving that this is not convergent, so I'm just going to assume that it is convergent. Okay? Let's say then, well, here's the idea. Now I want to do some math here. If this is to happen, after finite time, y sub n is going to be within an epsilon that I can choose arbitrarily small to be arbitrarily small of y infinity. But I know that y sub n is either 1 or minus 1. Let's write it like this. Then for, let's say, epsilon 1 over 4, that's a positive number. There's a time such that after this, time that I have, y sub n minus y sub infinity in absolute value is bounded from above by 1 over 4. Okay. I just applied the definition of what it means for y bullet to converge to y infinity using the specific error margin of 1/4. But you see, this is a symmetry property of the underlying metric that is actually doing the hard work here. Initially, we were thinking of this y sub n to stabilize at y sub infinity, but ultimately that means that the distance between these two things is at most 1/4, which also means that this supposed target would have to be within 1/4 of this term. And I know that if I take an n, this y sub n is going to be either 1 or -1 based on the given definition. And the next term, y sub n plus 1, is going to be the other one. Let's say in fact, I can do this. I can write this in a couple of ways, trying to come up with the perhaps most accurate or easiest to understand way to write things. No, let's write it like this. And opening this absolute value, I have this. Right, because some number in absolute value is bounded from above by 1/4, if and only if it is bounded from above and below by 1/4. And then reorganizing everything, I have this. So I'm continuing from here. Y sub n is either 1 or -1. It has two possible options. So I can do a case analysis here. If y sub n equals 1, then that means that y infinity is bounded from below by 3/4. But furthermore, I know that by the definition of the sequence, y sub n plus 1 has to be -1. And hence, since if this lowercase n is greater than or equal to capital N, then so is n plus 1, which means that the same expression, same bounds, hold for n plus 1 as well, which, if I were to use this, would tell me that y sub infinity is upper bounded by 1 plus, or -1 plus 1/4. Which is -3/4. And this consequently gives us a contradiction, because I'm saying y sub infinity is a real number that simultaneously is greater than 3/4 and less than -3/4. Which is a contradiction. We had assumed here that y sub n is 1. If you want to be technical, you would write an addendum to this, describing what happens if y sub n is -1. In fact, let's do it for this time. If, on the other hand, y sub n is -1, then y sub infinity, based on the same argument, is bounded from above by -3/4, but then y sub n plus 1 is going to be +1, in which case y sub infinity has to be bounded from below by 3/4. One. Again, a contradiction. And now, instead of writing these two cases after this stage, what you can do is, instead of writing these two special cases, you could say here, without loss of generality. Instead of writing this part, you would write here log, without loss of generality. This means, well, I have two options, two cases, but both of the arguments are going to be pretty much the same arguments because there's some symmetry involved. And so you say, without loss of generality, I can assume that y sub n is 1. So this is without loss of generality. When you're reading things, you might also see, we may assume this, that, the other thing. Okay. So in a sense, what was the tactic before writing these? It's what your colleague suggested, but the idea was this. Ultimately, this is a sequence that alternates between 1 and -1. In principle, or in particular, it means that this sequence hits 1 infinitely often, and it hits -1 infinitely often as well. And based on this, if the sequence is to converge, is to stabilize at any position, well, that position has to be very close to this point that you hit infinitely often, and it has to be simultaneously very close to this point that you hit infinitely often. And what I did is, well, I said, if I were to choose my error margin to be 1/4, if this sequence is to stabilize at a point, that point has to be within 1/4 of 1 and simultaneously within 1/4 of -1. But this cannot happen, I said. That's sort of the intuition behind the proof I wrote. Any comments or questions about this? Okay. Let's do one more example. I'll leave this. Z bullet, let's say, is defined by n goes to 2 to the n. Now you see this guy this time doesn't converge to a real number, but if you were to interpret it as a sequence of extended real numbers, you could say that this converges to infinity. Okay. So n extended reals. And how can I prove this? Well, I can say for any supposed upper bound, if I wait long enough, z sub n is going to exceed, is going to keep exceeding that supposed upper bound. Let's let m to be a positive number, supposed upper bound. Well, we know by the Archimedean principle, there's an integer that is greater than m. And in fact, I can write it like so. Take my upper bound m, Archimedean principle, it's an axiom, we're taking it, that we assume, says that there's an integer that exceeds this supposed upper bound. But of course, if some integer exceeds this m, any consecutive integer too is going to exceed. And I'm going to leave the next part to you. N is dominated by 2 to the n. You can show this using induction if you want. So this is an exercise. That's the end. So in a sense, one could say here z bullet converges to infinity, or you could say z bullet diverges to infinity. Right? When it comes, when the limits end up being infinity itself, then this convergence and divergence somewhat breaks up. Because in a sense, this does stabilize at infinity. Its asymptotic is determined in a sense. Not so much so for this example, for instance. This guy really doesn't converge. No matter whether or not you allow infinity to be a valid value. Okay. Any comments or questions? Yeah.
Can you reiterate the lowest line, the last line of it? It's an n?
N is less than or equal to 2 to the n. Oh.
That's m?
M is upper bounded by n by the Archimedean property. But then for any lowercase n that is an integer greater than n, well, this has to happen also by definition. But then n is upper bounded by 2 to the n, which is the nth term of my sequence. Yeah. Any other comments? Okay, so we have two, let's say three perhaps, major theorems. In fact, two of them are sort of restatements of each other regarding sequences of real numbers. Because somehow the convergence properties of sequences of real numbers end up being sort of the quintessential theorems that you would want any type of sequence to have, whether it be a sequence of functions or something else. So that's why we establish these theorems, at least for real numbers. So these theorems are based on simpler types of motion when it comes to sequences. Okay? The two types that are very important for sequences of real numbers is monotonicity. So you're not sort of jumping up and down. You're always going in one direction. And the other important behavior is boundedness. There's an upper limit to your sequence. So we first start with this monotonicity property. Okay. So, and this is called the monotone convergence theorem. It says this: if you have a non-increasing sequence of real numbers, then it always converges, and it converges to the inf of the set of terms. And likewise, if you have a non-decreasing sequence of real numbers, it converges to the sup. Let X bullet be a sequence. Then if, oh, I'll write it like this. Part 1. If X bullet is non-decreasing, i.e., for any time n, I want x sub n plus 1 to be not to the left of x sub n. I want it to be to the right or possibly the same. Of course, we're assuming that positive infinity is in this direction, negative infinity is in this direction. I'm going to call X bullet non-decreasing if at time n, if you're here, well, at time n plus 1, you can only go this way. You don't go that way. You can repeat the same position, but you're always moving in this direction. And so what I can write it, I can write it like so. Okay. You might also see the phrase monotone increasing. Then limit as n goes to infinity of x bullet, x sub n is the sup of x sub n, which is possibly an extended number. That's the first part. The second part basically says the same thing, but instead of non-decreasing, you look at non-increasing. And instead of sup, you have inf. Is non-increasing, i.e., for any time any consecutive time is to the left this time. Then again, limit as n goes to infinity of x sub n is the inf of x sub n which possibly this time is minus infinity. So if you were to think about 1 over n, for instance, as the example, we had shown 1 over n to converge to 0. But 0 is also the infimum of the set 1 over n as n varies among positive integers. So this is a, you see, static object. There's no motion here. You just listed down all possible positions you could have ever been under 1 over n. So this is static parts. This is a dynamic parts. Okay, this is time dependent. You're saying in the case of monotone sequences, time dependent things, in a sense, are static. That's sort of the interpretation I have in mind. Okay. Any comments about the statements? I'm only going to do one, and I'm going to leave two to you, because the proof is pretty much the same. You just need to change certain things, but the general structure is the same. So I'm going to prove one. There are two cases. Either x bullet is bounded from above or it's not. Okay. Or it's not. If it's not bounded from above, right? If x bullet is not bounded from above, well, then by definition, that means that the sup on the right-hand side is infinity. Then I'll just write it. By definition, sup of x sub n is infinity. I need to show that the limit is infinity. But of course, again, by definition of x bullet not being bounded from above, again, by definition, for any supposed bound, I'm going to exceed it. One has to be a little bit careful here. Oh, no, it's OK. There's an n such that x sub n exceeds m. But now, since I know that x bullet is non-decreasing, any lowercase n greater than uppercase n is going to be to the right of x sub n, which means that any subsequent term 2 is going to be exceeding uppercase m. But then, by monotonicity, for any n after uppercase n, this, and this is what it means for x bullet to converge to infinity, i.e. X bullet converges to infinity, and this was what we were trying to show. This case is done. There is the other part of x bullet being bounded, which we're going to do tomorrow. Okay? We're not done with the proof. But thank you. That's it for today. All right, let's start. Good morning. So we still have a couple things to discuss regarding sequences. I want to finish the proof of monotone convergence theorem. then we're going to switch over to a sort of related idea, related theorem. It's called the nested interval property. And then we're going to move on to subsequences and the famous Bolzano-Weierstrass theorem. OK, so monotone convergence theorem says this. I wrote it again. I have a sequence of real numbers. If your sequence is non-decreasing, which means that if you go forward in time, you're moving to the right in the real line. So jumping like so. You could repeat in principle. So this is not a strict inequality. But the point is that you're not going to the left for sure. You're moving only in one direction. Then, well, the limit exists. And it is a soup. This soup could be infinity or a finite number. But in any event, this equality holds. And certainly, if instead of going to this direction, if you're going this direction, to the negative infinity, again, you have monotonicity. And that's the second part. In this case, instead of saying the limit converges to the soup, you say it converges to the inf. In which case, inf could be minus infinity, but not a positive infinity. So these are analogous statements. The idea is the same. And that's why I'm just going to prove one. And I'm leaving the second item to you. So what we did was the following. We said, well, if I were to take a sequence, x bullet, of real numbers, exactly one of the two is going to happen. Either it's going to be bounded from above, or it's going to fail to be bounded from above. These are the only two cases. Exclusive or. Either this, x, or this. These two cannot happen simultaneously. This is perhaps a slightly easier case. If it is not bounded, then by definition of the supremum, this right-hand side has to be infinity. That's what it means for soup of x sub n, as n sort of varies over positives or non-negative integers, being infinity. That's what it means. And furthermore, by the definition of unboundedness of x bullets, I have that for any bound, supposed bound, there is some time such that x sub n exceeds m. Again, this is the definition of x bullet being unbounded. And at this stage, what I can invoke is monotonicity, the non-decreasing nature of x bullets, and say that, well, if at time capital N, x sub capital N exceeds m, then certainly after this capital N time, too, the same thing is going to happen, because after this time, x sub n cannot go to the left. It's going to go always to the right, possibly. And so once I have this lower bound, this lower bound is going to work for any time after this capital N, which, again, is a definition of what it means for the limit as n goes to infinity of x sub n to be infinity. And so in which case, I was able to show that both the right-hand side and the left-hand side are equal to infinity. That is to say, they're equal to each other. So that's the conclusion of this part of the proof. OK? So we need to do this part also. Now, in this case, because we're assuming that x bullet is bounded from above, well, by the definition of the supremum, that supremum has to be a finite real number. Then let's call it alpha for simplicity. It's a real number. It cannot be infinity. By the definition of the soup, this is going to be an upper bound. So for any n, x sub n is bounded from above by alpha. But I want to show that it's the limit as n goes to infinity is this. So what can I do is, what I can do is the following. So let epsilon be positive. Since alpha itself is a sup, I know that alpha minus epsilon, which is a strictly lesser number, is not the sup, which means that there is some capital N such that x sub capital N is between alpha and alpha minus epsilon. Then maybe I can be a little bit explicit. Since alpha minus epsilon is a number strictly less than the sup of x bullets, right? There is some capital N such that x sub capital N exceeds this. And certainly x sub capital N is going to be upper bounded by alpha, which is upper bounded by alpha plus epsilon. The point of writing it like this, of course, is that well, I'm going to rearrange things so that I have sort of like a distance-like expression here. Again, by the nature of x bullet being non-decreasing, once alpha minus epsilon is a lower bound, the same lower bound is going to work for any consecutive terms, any subsequent terms. So by monotonicity, for any n after capital N, alpha minus epsilon lower bounds x sub capital N, which itself lower bounds x sub lowercase n. And then we have these. But then I can just look at the middle term here and the two n terms, collect alpha here to see x sub n minus alpha is bounded from below by minus epsilon and from above by plus epsilon. That is to say, x sub n minus alpha in absolute value is upper bounded by epsilon. That's what it means for x sub n to converge to alpha. Make sense? Comments, questions? Now you see, the point is that even though the idea is the same, there are multiple ways of presenting the same idea. You can use like more words, less words, things like this. Part of this course is to give you an opportunity to sort of experiment with different styles and sort of see what works best for you. Okay. So, an immediate consequence of this monotone convergence theorem is this nested interval property. Now we're going to take a sequence of closed and bounded intervals, I bullet, okay? And what does this mean? This means that for any n, there is some lambda n and rho n real numbers, such that I sub n is this. And if you want to be more careful, you would also add this. Let's say specifically that lambda n is to the left of rho of n. So lambda is the left endpoint, and rho is the right endpoint. But depending on the index, depending on the time, these endpoints could be varying. Okay? It has two parts. I'm going to do one part. The other part, again, I'm going to leave to you. It says this. If I bullet is non-increasing, then their intersection is non-empty. they have a common point, at least one. And perhaps let's be clear about what this means as well. Maybe I should ask you, even if you don't see, even if before seeing the definition of what it means for such a sequence to be non-increasing, what could it mean? Let's try to guess. What could it mean for a sequence of intervals to be non-increasing?
Maybe the upper bound doesn't increase.
Okay.
Because it's of intervals, right? Not numbers.
In a sense, yes. Any other guesses? So you want to look at the name. It says nested. So that should be related to intervals being nested. So this means for any n, if I look at the interval at time n, it cannot be smaller than the interval at time n plus 1. Okay? So what is happening is something like this. Yeah? Yeah, what this says is that if you have infinitely many sets like this of a specific type, closed and bounded intervals, then there's an intersection. There is a common point that is included in all of these. That's what this says. Okay. The second part is an addition. If in addition, let me write it. Limit as n goes to infinity of L of I sub n, I'm going to define what this means, is 0. Then there's a unique point in this intersection in R such that the intersection is exactly this. And what is this L of the interval? This is nothing but the length. So the max minus min. Okay, this is length of I sub n, which is max of I sub n minus min of I sub n. Okay, and again, I'm going to leave the second part to you. This is, I don't think this is in the textbook, but the proof of this is not significantly more sophisticated than the proof of this. Okay. Comments or questions about this, about the statements? Let's first perhaps try to visualize what is happening. Maybe something like this, right? So something like this. This is a very special case of this. But you have this guy, and then like this, dot, dot, dot. And because of this, when you take the intersection of all of these, you get only 0, for instance. Yeah? That's an example of what this could mean. Of course, in this case, things are rather nice because these are sort of symmetric in a sense. And I'm just like zeroing in onto the center. But what could happen also is something like this, perhaps. I can also look at, let's say, j sub n. So minus 1 minus 1 over n, 1 plus 1 over n. To this sequence too, the theorem applies, for instance. in this case, you see, once you take the intersections of all of these, you're not going to get a single point. You're going to get a whole interval, in fact, right? Because here's -1, here's 1. And j sub n is something like this. Yeah? And as you increase n, what ends up happening is you're sort of like closing down on this whole interval. Okay? J sub n is -1 to 1 when you take the intersections of all of these. Make sense? So you see, that's the difference between 1 and 2. In 1, these are nested. When I take the intersection, there's at least one point. There's a unique point, indeed. And the reason why there's a unique point, the theorem says, is because the lengths go to 0. Not only they are nested, but the length of these, which in this case is 2 over n, goes to 0. So if you have nestedness and the length, or the diameter if you want, going to 0, then you have that in the intersection there's a unique point. In this case, there is nestedness, there is points in the common intersection, but there are multiple points in principle. Okay? So for instance, the length of j sub n is this minus this. So it is 2 plus 2 over n, and 2 plus 2 over n doesn't go to 0. Okay? And so I'm trying to sort of exemplify how you parse statements like this. Before sort of delving into the proof, you want to have an idea as to what type of things, what type of objects the theorem sort of applies to, supposedly. And what is at stake? Well, what could happen is your intervals could be nested, but maybe they sort of like move around a little bit like so. So we cannot just look at these sequences. We need to come up with sort of like an arbitrary sequence. Okay. Well, in a sense, I'm just going to use a definition of the closed and bounded interval, which I wrote over here. Since I0 is a superset of I1, which itself is a superset of I2, and so on, well, if I were to think of these as lambda n rho n, well, I have that the left endpoints constitute a sequence of non-decreasing numbers. And likewise, the right endpoints constitute a sequence of decreasing or non-increasing real numbers. So what you can do is you can say okay. But then if that is the case, I can think about the sequence of left endpoints as a sequence of real numbers in and of itself, apply MCT to deduce that it converges, and it converges to the sup, which has to be finite because any lambda I is bounded, say, by rho 0. So lambda bullet is a sequence of non-decreasing real numbers that is bounded from above. Therefore, it has to converge to the sup, which is a finite number. Is a bounded sequence, bounded and non-decreasing sequence of real numbers and hence, and so, limit as n goes to infinity of lambda sub n, I can define as lambda, I can define as lambda sub infinity. This is a sup of all of these. It's a real number. And similarly, I can say, using the second part of MCT, that rho bullet is a bounded sequence, and it's a non-increasing sequence, and therefore, by MCT, it also converges. Similarly, limit of rho sub n as n goes to infinity, I can define as rho sub infinity is going to be the nth. Again, a real number. And in fact, what I can write is something like this. In this sort of chain of inequalities, it's like so. Going back. The claim is going to be that the closed and bounded interval from lambda infinity to rho infinity is included in the common intersection. So let's write it over here. Continue from here. First, perhaps we can note that lambda sub infinity has to be to the left of rho sub infinity. So by definition of sup and inf, lambda sub infinity is going to be to the left of rho sub infinity. They could be equal in principle. Claim the interval from lambda sub infinity to rho sub infinity is in the common intersection. Since this is non-empty, we're going to be done. Well, the proof of this claim within the bigger proof, well, if I were to take an x, then x is lower bounded by lambda sub infinity and upper bounded by rho sub infinity. But lambda sub infinity has to be to the right of any lambda sub n by construction, because it's a sup of lambda sub n's. And likewise, rho sub infinity is going to be to the left of any rho sub n. Which means that x is between lambda n and rho of n for any n, which means that x is in I sub n for any n. That's what it means for a point to be in the common intersection. And that's the end of the proof. Of this proof and the general proof. This is the smaller proof, and which consequently finishes the general proof also. Comments or questions? Perhaps then let's think a little bit about how to handle the second part. So we have the proof of the first part. Now you also have the additional assumption that the lengths of the intervals go to 0. How can you justify that the common intersection is going to be only one point?
When inf and sup become the same.
Very good. So if you have this length going to 0, you need to somehow justify the fact or justify the conclusion that this then has to be equal to this. That's what you're saying. In other words, even though we wrote this as an interval, this is going to be equal to this. Okay? Because otherwise, you could say, if lambda sub infinity were strictly less than rho sub infinity, this interval would have positive length. But since this is contained in any of the intervals, when you take the limit of the lengths, this limit wouldn't be able to go to 0. It would be lower bounded by some positive number, which is exactly the length of this, in fact. Make sense? Very good. So that's how you do these kind of things. Let's try to perturb the statement, because I think this is useful. So when you see a statement like this, how far perhaps can you modify this statement to come up with different statements, or perhaps improve your understanding? Any guesses or comments? You want to think about the hypotheses and the conclusion. So I would suggest perhaps that you want to keep something like this. If you were to move this too much around, you're not going to be able to get a reasonable statement. You want to have something like you want to have a statement regarding the nature of the common intersection. That's what this theorem is all about, in a sense. You have a bunch of things, you take their common intersection, and this guarantees that under certain circumstances, this common intersection is not going to be empty. Okay? Now, first of all, for instance, if these intervals were not nested, well, you can just sort of like jump around like so. Then they're not going to have any common intersection. So that's too much. You have to keep this non-increasing property. Okay? You want to keep this as well. So somehow then, I would suggest that you want to perhaps perturb these. So you want to think about what could happen if, or how you could argue if your sequence of intervals were closed but not bounded, or were bounded but not closed. Okay, let's write these down. Another thing you can try doing is, well, you can say, oh, these two are hypotheses, and this is the conclusion. Well, assume the conclusion and see if you can go backwards. In other words, see if this and this is equivalent to saying this and this. Or rather, this implies this. I'll write these down. So example, or maybe exercise, in fact. So what if closed but not bounded? What if not closed but bounded? Oh, not closed but bounded. And then going backwards would be what in logic people call the converse. So converse. If I bullet is non-decreasing, oh, non-increasing, sorry. And the common intersection is non-empty, then can you justify or can you deduce that I bullet is a sequence of closed and bounded intervals? So in a sense, you're sort of testing how flexible this statement is. In a sense, you're sort of trying to figure out if the statement is sort of optimal within its sort of class, so to speak. And again, just like we did with the original statement, you want to come up with examples. You want to perhaps use, perhaps let's do this, the second part. Now I say, let I bullet be a sequence of bounded intervals. They could be possibly open. Then I say they are non-increasing. This still makes sense. Then the intersection is non-empty. Well, you would perhaps think of something like this. Say I sub n is minus 1 over n, 1 over n. Before we looked at the closed interval case, but now let's look at the open interval case. Make sense? Now this intersection is again non-empty. And in fact, it contains exactly one point, which is the origin. Yeah? 0 is included in any one of these open intervals. But you have to think a little bit more in this case, for instance. What could happen is something like this. So for instance, I can look at this one. 0 to 1 over n, open. This is again a nested interval sequence of intervals. So open, each of them are open intervals. These are certainly bounded. But you see the intersection of these is empty. Make sense? So just by sort of like trying to think about examples or trying to break this, the statements, you can try sort of perturbing the original theorem. Sometimes you're going to fail. So in this case, this just says that this doesn't hold. So this is false. You perturbed the statement, seemed like it could work, but you were able to come up with a counterexample here. But even if you came up with a wrong statement, I would argue that this still increases your understanding of this theorem. Now you know why closed is important here. Okay, you have a specific example that you say, oh, because if I didn't assume closed, this theorem wouldn't have worked. There are other situations where there's a bunch of hypotheses, not because without the hypotheses the theorem doesn't work, but possibly it's because the proof doesn't work. Maybe you need something else, right? In this instance, this justifies that indeed you need the closed assumption or hypothesis. And in fact, these two examples together also tell you that the converse is also false. Because this is a sequence of non-increasing intervals whose intersection is non-empty, but they are not closed, for instance. So the other way around also doesn't work. Goes one direction. Closed and bounded is an important hypothesis here. To get some element in the common intersection. And in fact, this duo, closed and bounded, is so important that people put it into one thing. They use the word compact. Okay. These two hypotheses, interval being closed and interval being bounded, together make so many things work that this thing has its own name, compact. Okay. So when you see the word compact interval, they mean closed and bounded interval. It's a faster way of saying the same thing. Any comments or questions? Yeah.
Could you quickly explain why I don't really understand why the first one with zeros in the intersection.
What does this mean? This means that for any n, 0 is in I sub n.
Yep.
Would you agree that 0 is in this interval for any n?
Well, I feel like if you follow the same line of reasoning, you get the open interval, and then they're the same and they're not contained. I don't know.
Well, in this case, the argument works. But so that's the thing. So for this specific sequence of open intervals, like you're saying, this argument would work. And it does say that the common intersection has a unique point in it. But the point is, if you were to take an arbitrary sequence of open intervals, the argument possibly fails.
Yeah.
Maybe you can rephrase your question.
I'll ask after class.
Okay.
Yeah.
So I guess maybe I can say it like this. You remember the Wason selection experiments or selection task. It says if closed and bounded and non-increasing, then the common intersection is non-empty. This doesn't say anything about what happens if it's open. If it's open, it can fail, it may work.
I get the logic part.
Okay. Okay. Yeah, maybe we can talk a little bit about this later. Yeah. Now, the true perturbation, really, of this statement is around the word interval. So somehow, people thought about the main property of what it means for an interval to be compact. Then they generalized that idea to an arbitrary subset. Then they started saying a subset is compact if something happens. And if you were to switch over to this without really looking at intervals, this still makes sense for arbitrary subsets or sequences of subsets. It turns out that, again, the intersection is non-empty. And this is what is called the Cantor intersection theorem. I'm not going to prove it, but if you're interested, you may want to have a look at it. Well, I'll write it here. And in a sense, I did point to this theorem, because the first picture I drew was sort of like a heat map type of thing. This picture kind of perhaps point to the idea that probably something like this holds for more general sequences and sequences of intervals. Probably this phenomenon has little to do with the fact that this is a sequence of intervals specifically. So intervals are sets that are very specific. Okay? Those of you who are going to take multivariable calculus or 3220, you're going to have to deal with this issue. In single variable, it's clear what a nice set is supposed to be. It's an interval. In multivariable, it's not as clear what a nice set is. Okay. We're not going to need these discussions in this class that much, though. Okay. Comments or questions? Okay. Now, in the textbook, you're going to see another phrase. I'm going to leave that. A sequence of real numbers is Cauchy if something happens. I'm going to postpone that for now because we're not going to need it for a while. We're going to really need this Cauchy property when we start talking about infinite series, so in the third part of the course. Until then, it's not very useful in my estimation, so I'm going to postpone that for now. So Cauchy sequence. Cauchy is a mathematician who was interested in the foundations of analysis, and he realized the importance of rigor and stuff, especially in analysis. Cauchy sequence. Later in infinite series parts. Part of the course. We're going to discuss it later. For now, I just want to say this. You can define what it means for a sequence to be Cauchy in any metric space. So, in any metric space, if a sequence is convergent, it is also Cauchy. So it's a property that is more general than convergence. Convergent implies Cauchy. It turns out that the other way around might fail in general, but for real numbers, in other words, for sequences of real numbers, this Cauchy property ends up being the same thing as convergent, and that's why I'm skipping it right now. We're not going to need it. In R, convergent if and only if Cauchy, and indeed, also for the types of sequences of functions that we're going to look at, convergence is going to be the same thing as Cauchy. Most function spaces. In most function spaces, convergent is going to be the same thing as Cauchy. Okay? So ultimately, because of these two things, it's going to be no issue to not talk about Cauchy property. It's a slightly more complicated statement. Again, it says something about the sequence stabilizing, but in a different sense somehow. Convergence is about stabilizing in an absolute manner. You have a target, and you talk about stability relative to that absolute target. Cauchy property is, again, some sort of stability, but you don't have an absolute target. You talk about relative stability. that's all I'm going to say for now. We're going to talk about how to visualize this and what the heuristic behind it is and all that stuff later. Okay. For now, this much is enough for Cauchy. What is more important at this stage is the so-called Bolzano-Weierstrass theorem. And to even state that, we need to talk a little bit about this idea of a subsequence. So remember, I mentioned this idea, subsequence, as one of the time modifications you can apply to any sequence whatsoever. Even before giving the definition, I want to give an example. Okay. So for instance, let's look at this. W bullet is a sequence of real numbers defined like so. N goes to n if n is odd. Otherwise, it's 1 over n. Okay. Let's try to visualize. Okay. As usual, the horizontal axis is my time. The vertical axis is my space. So 1, 2, 3, 4, and so on. That's 1. It's like this, like so, and all that. Yeah. So this is like a sequence that is spliced, so that I sort of created using a sequence that goes to infinity, this n sequence, and then 1 over n, that goes to 0. Okay? So you want to say something like this. In principle, or in general, let's say, W bullet doesn't converge to anything. It's a divergent sequence. It doesn't even converge to infinity, in fact. Right? Because for infinitely many terms, it stays away from infinity. Diverges. Even in extended reals. You can't even say it goes to infinity. However, what you can do is, well, you can edit out the type of behavior you wouldn't want to see to come up with a subsequence, we're going to say, that converges to something. Maybe I can draw it better. Like this. Okay, that's a better picture. Okay. This is my W bullet. This is time 1, 2, 3, 4, 5, 6, and so on. What I'm going to do is this. Okay. So imagine this is my footage. I'm not going to reorder different scenes or different frames. Imagine these are all my different frames. But I'm going to edit out certain frames I don't want to see. I'm going to get rid of this time, and this time. And I'm going to be left with some footage that goes to 0. That's the idea of a subsequence. I'm going to change the time. This is the intuition behind taking a subsequence. So we're going to have sort of sequences like this, and then we're going to edit out the types of behavior that we don't want to see. In this case, there's a blow-up going to infinity, We're going to say, oh, we're going to look at these times. We're going to get rid of those times. We don't want to see that behavior. We're going to just look at this convergent behavior that we want to see. That's the idea of a subsequence. Okay? We're going to continue talking about this tomorrow. Thank you. Okay, let's start. Good morning. So today we're going to keep working on sequences. We're slightly behind schedule, but it's not a major issue. We need to discuss this important theorem, Bolzano-Weierstrass theorem. So this is like one of the three main theorems when it comes to sequences of real numbers. And then, if time permits, we're going to switch over to continuity, continuity of functions. So let's first start with the definition of a subsequence, because Bolzano-Weierstrass, even the statement of it requires this notion. So this is one of those modifiers that you can apply to a sequence of anything, in fact. I'll write it like that. So if I take two sequences, x bullet and y bullet, in the same set, x. So let x be a set, and x bullet and y bullet be two sequences in x. I'm going to call y bullet to be a sequence of x bullets if the following happens. There's a j that acts on the time space, in this case non-negative integers, that satisfies the following two properties. First, I need to have that j is strictly increasing. In other words, if you want to be more explicit, for any integer, for any time, j of n has to be before j of n plus 1. Okay? The reason why is because sequences are temporal objects. These are dynamical objects. These are things that have futures. And so when you switch over to a subsequence, you don't want to mess with that notion of the future. You want to keep the arrow of time somehow. And so the idea of a subsequence, the way I think about it is, it's some behavior. So you start with your sequence, it's some behavior, but it does certain things, and you want to edit those out somehow. And so without changing the order in which things happen, all you get to do is to get rid of certain frames in your footage, if you want. I'm going to try to make sense of this a little bit more in a second. And so you need to have this so-called time change to be in the same direction. So the future has to stay the future. And so that's mathematically what that means. And j bullet is x bullet composed with j, which basically means this. Right? So for any time n, to figure out where y sub n is, well, you look at where x is at time j of n. That's the idea of a subsequence. In the textbook, and this is the more standard notation, you would see x sub n sub j. And here you're sort of letting j go to infinity. And so this would be sort of like a subsequence of x sub n. Either one of these are useful notations. I'm going to typically stick to this this notation that I describe here, because I like being able to sort of control the times I'm editing out and stuff. Depending on the context, you may want to be less explicit about this time change or more explicit and so on. Okay, that's the definition. And here's the example. I kind of started talking about this yesterday. I'm taking my time to be positive integers this time. It doesn't matter, as before, where you start. What matters is that you're going to the future. So the positive infinity. These are real valued sequences. W bullet at time n is n if n is odd, and 1 over n if n is even. Okay, that's a sequence. It's a well-defined sequence. Now, yesterday I visualized this using this space-time diagram. Horizontal was integer time, and vertical was the reals. Another way to sort of use or think about sequences that I hope is going to perhaps be helpful in the last problem and the problem set that is due this Friday is to use what is called the ticker tape notation. This ends up being helpful or useful, especially for sequences of real numbers. So ticker tapes were sort of things that people used to use back in the day in the stock market. So it's a little sheet of like paper, and so you write down the price of the stock, okay? And so there's a machine that keeps printing it out. And so if you're into stocks and stuff like that, there's typically sort of these like things that sort of go past in your screen, whatever. So it's like it goes like this, and there's a bunch of numbers for the same stock, and like this sort of strip keeps sort of like running that way to give you real-time information. So that's the idea of a ticker tape. But we can use this in this context as well. So what we can do is something like this, perhaps. Okay, this is like so. It's a tape, it's a ticker tape. I like sort of separating time 0, or rather time 1, and then 2, 3, 4, 5, 6, 7, and so on. So these are cells like this. And I'm going to populate the boxes. So this corresponds to time 1. Okay. So this is n, 1, 2, 3, 4, whatever. So at time 1, w, because 1 is odd, should have the value of 1. Okay. At time 2, well, n is 2. That means that w sub 2 is 1 over 2. Then 3, 1 over 4, 5, 1 over 6, 7, and so on. Okay. This is a ticker tape representation of the sequence. This is yet another way of perhaps visualizing or thinking about such a sequence. Okay. Does this kind of make sense? Okay, so let's think about the other ones. What you can do is you can sort of extend this. Like so. Then separate out more ticker tapes. So X bullet, Y bullet. Okay. Now at time 1, when n equals 1, x sub x bullet is just 1, and it keeps going like this. 1, 2, 3, 4, 5, 6, 7. Okay. Okay. And then, for instance, y bullet is 1 over n. So this is 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. Okay. Now, even though it might look like it, because somehow it kind of looks like I made up W bullet using these two sequences, times are important. Ultimately, if you're switching, if you're passing to a subsequence, you should not be able to get new values. But because of the fact that, for instance, using X bullet, at some time I'm at position 2, and with omega, or rather with W, I'm never at position 2, I cannot say that X bullet is a subsequence of W. Okay? And likewise, Y bullet is not a subsequence of W because, for instance, Y bullet at some time is 1 over 3, but W bullet is never there. Okay? So these are not subsequences of W. And certainly they are also not subsequences of each other. So, but then what I can do is perhaps to come up with examples of subsequences, I can, well, try using a strictly increasing function like this. So for instance, if I were to use j, that takes time to 2n, then I can look at, I'll do it here. Okay, let's say that this is W bullet again. I'm just going to record this again. 1 over 2, 3, 1 over 4, 5, 1 over 6, 7, 1 over 8, goes on like this. This is a strictly increasing function. J of n is 2n, and 2n is strictly less than 2 times n plus 1. So this is an admissible time change. And so if I were to look at W bullet composed with j, I get this. Okay, so maybe I can call this W bullet prime. Let's do a couple of them. So for instance, let's say that I'm trying to figure out where this new sequence is at time 1. In other words, I'm trying to figure out this number. Well, by definition, this is this. But then by the definition of j, this is W sub 2. Okay? And so I read off where my original sequence is at time 2. Oh, it's at 1 over 2. For this new sequence, you're going to be here at time 1. So you take this, put it there. Make sense? And I keep going like this. For instance, at time 2 for this new sequence, I need to be looking at time j of 2, in which case I should be looking at this one. So this would be 1 over 4, 1 over 6, 1 over 8, and so on. Okay? I'm not going to keep writing. So in a sense, what is the effect of passing from this original sequence to this subsequence? Well, I say, well, I'm just going to edit out these values. Odd times I'm going to edit out. Does this make sense? OK. So that's one example. Another example is something like this. K at time n goes to n plus 1. That's again a time change. OK. I can use that. Let's say here, let's say W bar bullet. That's a new subsequence. This is yet another subsequence, you see. This time, what you're doing, so at time 1, this new subsequence is going to be where the original sequence is at time k of 1. But k of 1, based on the definition, is 2. So again, I'm looking at this. But you see, things are slightly different this time, because if I were to look at where W bar is at time 2, then I need to look at k of 2 as time in the original sequence, but k of 2 is 3. So I'm going to, instead of taking this, I'm going to take this. Okay. So the effect of this second time change, k, is different. What it did, in principle, is, well, it just edited out the first frame. That's how I'm imagining this. It just said, get rid of this first entry. Shift everything. The first time change that we looked at said, oh, take every other frame. You can imagine this to be like a strip of film as well. this J time change said, take every other frame. Okay? K said, get rid of the first frame. Okay? There's a bunch of things like this you can do. In principle, you can compose J and K in either direction. So for instance, if I were to look at this, take n, add 1, and then double. So this is this. Or of course, you can do it the other way around. It's not quite the same thing. This time you're going to get 2n plus 1. These are all valid time changes, for instance. And in general, here's an exercise. If I were to take any two strictly increasing functions like this, their composition too is going to be strictly increasing. And so one of the games we're going to play in this class is going to be, well, I start with some sequence, but I want to get a certain behavior out of it. And we're going to start sort of editing out the behavior we don't like. So for instance, I have here this W, original sequence. Some terms blow up to infinity. I say, no, I don't want to look at that. I want to look at this nice sequence that converges to 0. So that's what we're going to do. Typically, what we're going to do further is that we're going to try to sort of combine a bunch of properties. So we're going to take subsequences of subsequences and so on. We're going to use things like this. Okay? Now, one difference is going to be that while sort of taking subsequences using strictly increasing functions that are explicit is something valid and useful, this ends up being more useful in a more applied context. In our situation, what's going to happen is we're going to have sort of like abstract conditions. And based on the validity of those conditions for certain times, we're going to edit out our times. Meaning our subsequences are not going to be specified as explicit as in this example, typically. OK. Any comments or questions about this? Now, the idea works the same when it comes to a sequence of functions, sequence of subsets, whatever. Okay? It just becomes harder to visualize what is happening. The big theorem, Bolzano-Weierstrass, says this. If you have a bounded sequence of real numbers, it may diverge or converge, of course, but it always has a convergent subsequence. I'll do it here. This is like one of the foundational results. And in fact, I was looking at one of these notes in the syllabus. I noted notes by Ulger. And there he says, he calls this the fundamental theorem of real analysis. I'm not sure if I agree, but I agree that it's very important. Bolzano-Weierstrass. These are, again, very famous mathematicians who are really interested in sort of making rigorous many ideas coming from calculus. So these are the old heroes in a sense. It says this. Let x bullet be a sequence of real numbers if x bullet is bounded, then it has a subsequence that is convergent. It has a convergent subsequence. It has a convergent subsequence. So the moment your original sequence is bounded, you get to edit out some behavior to get convergence. That's what it says. Okay? It doesn't say anything about uniqueness. It doesn't say a unique subsequence that is convergent. It also doesn't say anything about backwards. It doesn't say if a sequence has a convergent subsequence, it has to be bounded. For instance, this guy has a convergent subsequence. W bullet, it's not a bounded sequence, blows up to infinity, but it has a convergent subsequence. Okay? So Bolzano-Weierstrass doesn't say anything about sequences that are not bounded. It says if it is bounded, then it has a convergent subsequence. Okay? maybe we can think about an example as well before thinking about the proof. So what type of a sequence one could have in mind? Maybe something like this. Let's say z bullet n sent to -1 to the n. -1 to the n, we saw the sequence before too. It is a bounded sequence, right? So it is at most 1, at least -1. So it's a bounded sequence. It is not convergent. We saw that it is divergent, in fact. But you see, if you were to look at only odd times, so bounded, divergent, if I were to look at j of n, which is 2n, okay, then z composed with j is a constant sequence, in fact. Forget about being convergent. It's more, it is constant. Constant meaning convergent. Okay? If I wanted, I could have also looked at, for instance, odd terms. If I were to just focus on the odd terms of the sequence, then it would again be a constant sequence. I could have waited 10 billion time, meaning 2n plus 10 billion. Look at that subsequence. That's again convergent, whatever. So it has many convergent subsequences. Okay? But it has at least one. That's the point. Makes sense?
What if the function was just n mapping to n?
Very good point.
Does it still converge?
In this case,
Well,
what do you mean?
if we change the example and the sequence is just n mapping to n,
Okay. Is that bounded? It can't be. Yes.
so how would it converge if it's just
It wouldn't.
strictly going up?
It wouldn't.
Well, what would be the subsequence of that? That converges.
It wouldn't have any subsequence that converges. This doesn't say anything about sequences that are not bounded. Just says something about what happens if you have a bounded sequence to begin with. So you start with sort of like a sequence. You realize, oh, at least it is bounded. But maybe it may not converge, something like this. Then you get to edit out certain frames to get convergence. If you start with something that is not bounded, then, I mean, you're on your own. Okay? In this case, we were lucky. In this case, we were lucky and we had a subsequence that converged. But in general, like you're saying, so if you start with a sequence that is not bounded, n sent to n, let's say x, y, z, q, bullet. This is also an unbounded sequence, but as opposed to this, this has no convergent subsequences. Can happen. So if you start with a sequence that is not bounded, you're on your own. But if you start with something that is bounded, then this guarantees that there's a convergent subsequence. Okay. No convergent subsequences. So you have to start with something bounded. Yes?
Why is W bullet bounded?
It's not bounded. This is unbounded.
It's not bounded.
Yes, this is unbounded. Even though it is unbounded, it has a convergent subsequence. This is unbounded. This has no convergent subsequences. So if you start with an unbounded sequence, both can happen. You're on your own, that means. You have to really sort of think about what is really happening. Bolzano-Weierstrass says, guarantees, if you start with bounded, you have a convergent subsequence. Okay? So the fact that this has a convergent subsequence has nothing to do with Bolzano-Weierstrass. Okay? Yes.
How? How do you
Uh,
say? Wait. So just explain. J of n means z
2 times n.
2?
Yeah, this is 2.
Oh.
I'm saying if I start with this sequence, I'm going to do double time. If I do double time, actually the sequence now in this new time change, just doing the same thing. Right? My signal here is -1, 1, -1, 1. But if I do double time, it's going to be -1, -1, -1, -1. Yeah. Okay. So here's a proof. No, I understand all this stuff is these type of things are hard to think about, hard to get used to. In fact, I'll erase this part. So proof goes like this. There are multiple proofs, in fact. But this is, in a sense, the most intuitive one to me. It's slightly different than the proof given in the textbook, but it's the same idea, essentially. We're going to use the nested interval property that we established yesterday. By hypothesis, I know that x bullet is bounded, which means that there is an m such that x bullet is a sequence in the interval minus m to m. Write it like this. That's what it means for x bullet to be bounded. Okay. In particular, x1 is a certain point in this interval. Okay. Now I'm going to use this position to split the original interval into 2 pieces. There's a left part, right part. L1, let's say, is minus m to x1, and R1 to be the right side. Okay? Just going to draw the picture here too. All my terms are in this. Somewhere in it is x1, let's say here. Okay? The left side is L1. The right side is R1. Now I look at the next terms. I still have infinitely many times I can use. Either my sequence is going to hit the left interval here infinitely often, or it's going to hit the right interval infinitely often. At least one of these has to happen. Maybe both happen, because maybe the sequence just like alternates between the two. But it cannot be the case that both this and this are hit finitely many times. Then either m, let's say, such that, well, I'll write it like this. So this is the set of times after time 1 for which the sequence x bullet hits the left interval. Either there are infinite many times like this, or my sequence hits the right interval infinitely often. Okay. Both can happen too. I just need that at least one of these happen. Define, I'll keep this. Define I1 to be L1 if the first statement is true, and define it to be R1 otherwise. Okay. So you were here at time 1. Now I'm looking at time 2, 3, whatever, all the way up to infinity. I'm saying either I'm hitting this interval infinitely often or this interval infinitely often. Let's say you're hitting this infinitely often. Maybe you're hitting this infinitely often as well, but I don't care about this. But then I can apply the same reasoning to this interval. So how do I want to write this? Then there is an, let's say, n1 after time 1 such that x sub n1 is in I1. Define again L2, R2 as the two sides of I1. So min of I1 all the way up to x sub n1, and R2 to be x sub n1 all the way up to max of I1. By the very same reasoning I could have that I could use here, my sequence hits either L2 infinitely often or it hits R2 infinitely often. I'm just going to say here, by induction, we have a nested sequence of closed and bounded intervals, of closed and bounded intervals, I bullet, which means by the nested interval property, they have a common intersection. They have a common intersection. Okay. So what did happen here? I had an x1 like this. I'll draw this again. started like this. This was L1 and this was R1. For the purposes of drawing, let's say that I'm hitting the L1 infinitely often. So that I'm defining I1 to be L1. Then I said, if that is the case, there is some time after time 1 where x sub n1 is somewhere inside. Say it's here. Then I said, by the same reasoning, if I were to look at L2 and R2, at least one of these two sides is going to be hit by my sequence infinitely often. Let's say, for instance, for the sake of this picture, this one. So that now I'm choosing I2 to be this. And so there is some n2 after n1 that is here. And I keep going like this, right? That is the idea of the proof. Induction tells me that this is a well-defined operation for me. I can indeed do this. What I can then say is, to finish the proof, either I chose the right interval infinitely often, or I chose the left interval infinitely often. Okay? In either case, I have one monotone sequence that has to converge to the sup or inf of this common intersection. Write it here. So either I sub n, well, I'll put it like this. Either n such that I sub n equals L sub n is infinite, or the other way around. Either I chose infinitely often left intervals or infinitely often right intervals. In either case, looking at the appropriate endpoint of these sequence of intervals, I have a monotone sequence that has to converge, therefore. In any case, the endpoints, the appropriate endpoints of these intervals will constitute a monotone sequence which by MCT has to converge. And that's the end of the proof. This is probably the most complicated theorem we've seen so far. Yeah?
Does it always converge to the interval that you chose it to be infinitely what?
What do you mean?
Because you split the interval.
Yes.
The first one you chose the one L1 to have infinitely many points, right?
Yes.
And then the second level you choose R2 to be infinitely.
Yes.
Right. Then the convergent interval
Well, because they're nested.
will be also infinitely
Well, the thing is this, right? So what might happen is that this common intersection may have some positive length. That's one issue, and that's why I need to sort of add this part. I cannot just say, oh, then my subsequence that I obtain using these times converges to the limit, which is this, which is the common intersection, because I don't know at this stage. In fact, it's not necessarily true that the common intersection consists of exactly one point. If that were the case, I could have said that. But I am not guaranteed that the common intersection has exactly one point. It might have a positive length.
Okay, but you converge to some point within that.
Yes, that is true. Yes, that is true. Very good. Yes. Okay. Any other comments or questions? I realize that this, maybe I could have proved it a little bit more explicitly, but this is like a hard theorem to understand the proof of when you first see it. Okay. But the idea is the nested interval property ultimately, NIP. The point of this whole thing is to start with a sequence, and then using the terms of this sequence, come up with a nested sequences of intervals. That's all there is to it ultimately. Okay. So when we talk about proofs, or when we prove things in class, that means that typically these are sort of more complicated. And so I wouldn't ask you to reproduce a proof of something like this. This means that now this is technology you can use without any restriction. Part of why we're proving certain things and we're not proving certain other things is because, well, this is somewhat technical and complicated. So this is something that you can black box now. Okay, you can just say Bolzano-Weierstrass, whatever. Likewise for MCT here and NIP. These are all pieces of technology you can use without any restrictions now. That is not quite true for exercises, for instance. Exercises, I'm leaving them to you. Okay. Any comments or questions? Okay. Okay. So that's all I want to say about sequences for now. I want to transition now to continuity. Okay. I'll give the general definition in the context of metric spaces and then immediately specialize to the case of functions between sets of numbers. Because somehow continuity is all about, in a sense, distances, and more specifically perhaps, it's about preserving convergent sequences. Definition. Let x and y be two metric spaces, and f be a function from x to y. Let me also take a point. Let's say x star in x. I'm going to say that f is continuous at x star if either one of the following two is satisfied. These are equivalent statements, which we're going to discuss later. F is said to be continuous at x star if either one of the following statements is true. There are, in fact, many other ways of describing continuity at a point, which probably in the next problem set, which is going to be released not this Friday, but the Friday after, because we have the midterm next Friday. So in that next problem set, you're going to see a couple other characterizations of continuity, probably. If either, I can write it like this, for any x bullet converging to x infinity in x, or x star rather, the image sequence f of x bullet converges to f of x star. In y. Meaning, if you start with a convergent sequence that converges to x star, you want the images to converge to the image of x star. That's one way of saying it. Another way of saying it is this epsilon delta definition. For any epsilon, there is a delta such that for any x in x, if the distance between x and x star is bounded by delta, then the distance between f of x and f of x star is bounded by epsilon. Often, the first characterization is a lot more useful, very convenient to use sequences. The one trade-off is that it's not as geometric and intuitive as the second one. Okay? So we're going to talk about the equivalence of these two statements later on Friday. I want to finish off by stating continuity for functions between subsets of reals. If x and y were subsets of the reals, and again, I'm thinking about a function from x to y, then opening this up says this. For any epsilon, there's a delta such that for any x in x, x minus x star in absolute values less than delta implies f of x minus f of x star in absolute value is less than epsilon. I just wrote down what this means, d of x and d of y, using the standard metric of the reals. Okay. I have, I think, 2 minutes or something. I'll add a couple more definitions. I'm going to call f continuous if it is continuous everywhere. At x star for any x star in x. And the set of all continuous functions from x to y is going to be denoted by C0 xy. this is our first function space. This is going to be. We're going to spend a lot of time with this. OK, that's it for today. Thank you. We're going to continue on Friday. All right, good morning. Today we're going to do some stuff. Question? Sorry. One thing is that I forgot to tell you about some of these ideas. The main important thing is this limit inferior and limit superior. These are related sequences of real numbers. While in principle and in practice they're rather useful, from the last time I taught this class, I realized we don't quite use these ideas that much. So I'm just going to fast forward these. So I want to discuss a couple of things. And then I want to talk about this continuity. We had talked about, we defined what it means for a function to be continuous at a point. I gave two equivalent conditions. But we need to verify that they're equivalent. Because somehow verifying the equivalence of these two statements is sort of like a rather useful method that we keep using quite often in this course. So first, this idea of this tail sequence. If I start with a set x and a sequence, x bullets, then what you can do is you can look at the sequence of the tails of x bullet. T bullet now is taking values in the collection of subsets of x. At time n, well, you're just going to tally up. You're just going to consider the collection of all positions that your original sequence visits after time n. That's why this is called the tail sequence. So the image of x bullet is the same thing as t0. But then t1, all the places you visit, starting from time 1, is a subset of t0. Possibly equal, but it could be strictly less. And then t2 is the second tail, all the positions you visit after time 2, and so on. So just to give an example, for instance, if my x bullet is 1 over n, then t sub n is going to be 1 over m, where m is at least n. OK? So when people talk about, for instance, in the context of probability and stuff, tail events and stuff like that, essentially they're trying to refer to something like this. Typically in probability, things are more complicated, of course. But this is sort of the general idea. And based on this, we have a couple of things. On the one hand, we have this exercise, which I'm calling the Monotone Subsequence Lemma. If I have a sequence of real numbers, exercise is to show that there's a subsequence of x bullet that is either non-increasing or non-decreasing. Okay? And the idea behind this is this. You look at the tail sequence, and you say, oh, there are two possibilities exactly. Either for all time, max of nth tail exists, or the exact opposite. Namely, there is some time such that the max at that time, max of the tail at that time doesn't exist. You have to do something about this. This is not super straightforward of an exercise, but we can talk about it later. The main use of this is that using it together with the monotone convergence theorem, you can come up with yet another proof of Bolzano-Weierstrass. Any bounded sequence, remember, has a convergent subsequence. Any bounded sequence of real numbers has a convergent subsequence. So once you establish this, that gives you another proof of the Bolzano-Weierstrass. That is slightly distinct from the one that we discussed. OK. Now, the idea of limit inferior and limit superior, well, let me first define them and then try to give you an idea as to what these are trying to do. So the notation for limit inferior is liminf, okay? And the notation for limsup is limit superior is limsup. As usual, I take a sequence of real numbers. And the limsup of the sequence is defined literally as the limit of the superiors. Okay? Limsup is defined as limit of sup. I'll say what this means in a second. Another way to do this is like so. These are possibly extended real numbers. They always exist. Okay? So here's the idea. You look at the tail sequence. By definition, okay, the tail sequence, it's a sequence of nested subsets. Okay? As you let time go forward, you're going to have possibly smaller subsets. Okay? But we also talked about how, well, the sup and inf of a larger set has the upper and lower bound, the sup and inf of a smaller set. Which means, because of this nested property, no matter which sequence I start with, I have this. This is a bigger set than this, which means that the sup of this is larger possibly than the sup of this, and the inf of it is going to be lesser than this. And so I have inf of t0, which in principle could be minus infinity. Which is upper bounded by the inf of the first tail, which itself is upper bounded by the inf of the second tail, and so on. Okay? I'm just using the fact that these tails keep getting smaller and smaller. And this was something that we had proved a while ago. Right? So the idea was, if you have a smaller set inside a larger set, for the larger set, the sup has to be greater. And likewise, the inf has to be greater. Inf has to be lesser. But by the same reasoning again, I have also that the sequence of sups is non-decreasing, or rather non-increasing. And again, in principle, the sup could be positive infinity. Okay? So in this definition, when we write this, this inner inf is nothing but the inf of the nth tail. I just look at where my sequence visits after time n, and I look at the inf of that set. So this is inf of t sub n. And likewise, this is the sup of t sub n. But then, since the inf of the tails is a non-decreasing sequence, and the sup of the tails is a non-increasing sequence, by monotone convergence lemma, or monotone convergence theorem, I know that these limits exist. Okay? And because the inf of the tails is non-decreasing, limit has to exist, and it has to equal to the sup. And likewise, because the sup of t sub n's is a non-increasing sequence of numbers, by the monotone convergence theorem, the limit of the sups of the tails exists, and it has to equal to the inf. Okay? So this is the definition of these two things. comments or questions about this? The benefit of using these is, well, the way I think about it is that they allow me to take limits of sequences even when the sequence is not convergent. And again, I'm going to compile the relevant results into one exercise. These are in the textbook. Not very important for us, I think, but they're still useful results. So let's write it here. Exercise. Let x bullet be a sequence of real numbers. Then well, first of all, there is a subsequence of x bullet that converges to this extended number, liminf. There's yet another, possibly different, subsequence that converges to limsup. There are subsequences of x bullet that converge to liminf and limsup. If you have a subsequential limit, in other words, if there's a number such that some subsequence of x bullet converges to that number, then that number has to be between liminf and limsup. If x star is a real number such that some subsequence of x bullet converges to x star, then x star is lower bounded by the liminf of x bullet and upper bounded by the limsup. Then x star is in the interval with bounds liminf and limsup. And finally, x bullet converges if and only if the liminf and limsup are the same number. Converges if and only if liminf is the same thing as limsup. And of course, I need these to be real numbers, not extended. It's a mouthful. It looks very scary when you first see these. But I assure you, the establishment of these is nothing but sort of writing down the definitions and moving the logical quantifiers around. These are fairly general statements. And like I said, we end up not really using these in this course. Just to give an idea, a nice example. So for instance, liminf of -1 to the n, you see the limit of the sequence doesn't exist. This is not a convergent sequence, but this is sort of, I imagine it like this. So what is the sort of asymptotic behavior that I see? Asymptotically, you hit -1 infinitely often and +1 infinitely often. Heuristically, then, the liminf of the sequence should be -1. And limsup is going to be +1. Well, I guess I don't need the parentheses. Okay. Any comments or questions about this? Yeah.
When you define limsup or liminf, you don't care about subsequence of x0, x Boolean, right?
Yeah, yes, exactly. That's in the definition. It's not that clear how subsequences are related here.
Right. But then from that, you do care about subsequence.
Well, yes, that's part of the exercise. You need to open up this definition. And from this, you need to figure out a subsequence that really converges to this thing. Yeah. So this is where the engineering of, getting rid of unnecessary times come into play. It's like when I say there is a subsequence, and if this is something to be proven, you need to give me the times. Right? So subsequences are about like extracting out certain times where certain behaviors happen. It's like you need to engineer for me the times. Yeah. Very good. Okay. Okay. Continuity. Now this equivalence I had mentioned on Wednesday applies to functions between any two metric spaces, but I'm not going to write it I'm not going to prove the equivalence in this more general setting. I'm going to leave that to you. Instead, I'm going to focus on functions defined on subsets of reals. Okay. So recall, for x and y subsets of the reals, and a function from x to y, and x star, a specific point in x, f is continuous at x star if either one of the following statements hold. If one of the following equivalent statements hold. Equivalent statements hold. First statement, I'm not going to use this metric notation. I'm going to use the sort of absolute value of the difference notation. The first one is the so-called, I guess the first one was the sequential thing. For any sequence explicit that converges to x star, the image sequence f of x bullet converges to f of x. So the image sequence f of x bullet converges to f of x star. That's the first. Second is the epsilon delta definition. For any epsilon positive, there is a delta such that for any x in x, if the distance between x and x star is bounded by delta, then the distance between f of x and f of x star is bounded by epsilon. Okay. That's a statement. What I want to do is, I want to really establish that these two statements are equivalent. One implies the other one and vice versa. Okay. But even before that, I think I want to talk a little bit about why this is the correct definition of continuity. Because somehow, when you first see this epsilon delta definition, it feels like maybe for continuity, epsilon should be here and delta should be there. Or maybe it should be going the other way around somehow. So I would like to first try to convince you that this is really the appropriate order in which things ought to be written. There's an intuition behind item 1 as well, but I think figuring out item 2 is it is a much more intuitive statement in a sense. Oh, I should mention PSET 2 grades, and so I'm hoping to release PSET 2 grades and the solutions today. And by the end of today, you're going to get a guide for midterm 1, which is next week. I forgot to tell you. So epsilon, okay, is again this error margin, but the order of thinking is sort of like backwards in a sense. In other words, say you're sort of preparing for the exam. Continuity doesn't quite match with this idea of, well, I have this many hours to prepare for the exam, and I will prepare however much, and whatever I get, that's going to be it. That is not continuity, okay? Continuity works backwards. You say, you first set your goal. What is my goal for this exam? 95%, whatever. Then, based on that, you figure out how much you should be studying. It works backwards, okay? Here's a picture that I have in mind. We use arrows like this to denote functions, but in a sense, this analogy, this notation is rather very evocative. Okay, so here's my x, and here's my y. Here's x star, here is f of x star. And f goes from x to y. Okay. Now I want you to think of the function f as someone like an archer, okay? And you're doing target practice. You are given that, and so you should think of different points in this x to be different sort of configurations or different initial positions you take. Things like how far you're sort of pulling the archer, the bow, or maybe where you're sort of like pointing at, all of these things. Somehow, you're given that x star goes to f of x star, but this is somewhat like an idealistic, it's an idealized sort of arrow. What you really try to do for continuity at x star is to, as usual, first allow yourself some error margin. Okay? So in principle, if you were sort of this amazing archer, you could exactly hit, starting from here, you could hit this bullseye. But let's say that you just started your training in archery. And so ultimately, even though you want to hit f of x star, if you want ultimately you want to hit the bullseye, well, if you're trying to practice, you don't start there, right? You first start with, well, perhaps trying to hit the target to begin with. This is like similar to the idea of this convergence of a sequence. We're going to start with some error margin, and then we're going to want to shrink the error margin as much as possible. That's always the idea. So you fix your epsilon, and as you're training, you say, well, if I control how I'm shooting my arrow within some delta, then somehow I am guaranteed that I'm going to land within this epsilon target. Okay? So you say, given epsilon, there is a delta such that any x within this delta goes to some point within this epsilon. Of course, when you apply f to this, it's probably not going to stay as a disk like this. But you still want it to be inside. Okay? So this guy is the image of this set, delta ball, let's say. Okay. Any questions about this? But the point, of course, is just like with the convergence of sequences, you don't want to just say for some epsilon, say for instance epsilon equals 1, you want to say also for epsilon equals 1/2, epsilon equals 1/4, epsilon equals 1/8, and in principle epsilon equals 1/2 to the n. Say. So you would like to be able to keep shrinking this epsilon, but you still would want to be able to control how you're shooting your arrow so that you still hit this epsilon target. That is continuity. In any setting, this is how continuity works for matrix spaces. Okay. Does this kind of make sense? This is the intuition I have. Yes?
So it seems like you set epsilon first.
Yes.
And then delta is a function of epsilon.
Exactly.
But here your error is toward right.
What do you mean?
Yeah, with that concept, I would say this arrow should point left.
Well, yes, but what you want to say is if I control how I'm shooting the arrow within some delta, that is a function of epsilon, like you're saying, then I am guaranteed that I'm going to shoot my arrow to within an epsilon of the actual target.
So that's the thinking, and this is the expression.
Yes.
Someone.
Yes.
Okay.
Yes.
So it says that there exists a delta, so we only need one
Well, okay, that's a good point. If there's a delta such that this happens, of course, if you were to shrink delta, let's say delta over 2, the same statement would still hold. Think about it, okay? Think about it like this. I'll draw this again. Okay. X star, here is f of x star. I fix my error margin epsilon. I want to say if I'm sufficiently close to x star, my arrows are going to land to this epsilon target. Say this function is continuous at this point, so that you can actually do this, that there's at least one delta, given epsilon. Okay? In fact, let's do it like this. Fix epsilon to be 1, okay? It's a specific number. Say there's a delta for this specific epsilon, okay? There is a delta, okay? Such that when you throw any point in this delta using f, you land somewhere here. In other words, you take this x, let's say, apply f to it, you land somewhere here. Okay? Now, if you look at all possible points, well, it's going to be a certain subset of this epsilon target. Yes? So maybe something like this. F of, so the image. I won't write it. But then, if you can accomplish this, what if you were to halve this delta? Let's say you trained better, and you can control your bow better. Well, if you had a smaller delta, say delta over 2. Okay. Now this orange guy is going to land, by definition, essentially, to somewhere that is a subset of the image of the blue subset. So that's going to this is how it's going to look like. Which means that since the blue subset is a subset of the epsilon target, you're free, once you have a delta, you're free to shrink it as much as possible. Yes. Any other comments or questions? This is always the intuition, okay? And in a sense, this is somewhat compatible with the intuition for sequences, or rather their convergences as also. When you're writing proofs, what ends up happening often is you're going to realize, well, if you read in a textbook or if you see my proofs and stuff, typically I say, let epsilon be positive, and then I do things. But often, it ends up being more useful to start with what you're trying to control and somehow write the proof backwards. Okay? Understanding or being able to use statements like this is a major part of this course. So if you're sort of feeling shaky, or if you're sort of questioning things, that's perfectly natural right now. So, before giving examples, I want to verify the equivalence of these two statements. Okay? Well, maybe in fact, let's try to draw one more picture. Because this somehow is a general picture that's going to work. But let's also try to figure out how this continuity would look like if x and y were intervals. Oh, yeah, go ahead.
So if we were to want to try and prove something about the convergence of some function to some point, our duty then is to find some delta?
Yes.
Okay.
Yes. You need to engineer delta given an epsilon. Yeah.
Thank you.
So this is one picture. This is the general picture. So now let's imagine x, y are intervals. So that maybe now I can try to draw the graph of f and try to visualize what this epsilon delta is all about. And in fact, let's say both x and y are the whole reals, okay? To simplify. We're going to look at the graph of f. Somewhere here is x star. And my function, or rather its graph, passes through x star, comma f of x star. So I don't know the graph of the function, but I know that at least it passes through this point. Okay? Now, in this picture, epsilon controls the height, delta controls the width. Okay? So I take an epsilon, and ultimately, you see in this picture, f of x and f of x star, you want to think of them as heights. So I look at f of x star plus epsilon. It's some number greater than f of x star. And f of x star minus epsilon. Okay? And again, remember, in the case of real numbers, of course, saying that the absolute value of something is bounded from above by epsilon is the same thing as saying that this number is bounded from above by epsilon and from below by minus epsilon. In other words, rearranging, that means that f of x is bounded from above by f of x star and bounded from below by f of x star minus epsilon. Okay, I'll write it here. This is the same thing as saying that f of x is upper bounded by f of x star plus epsilon and lower bounded by f of x star minus epsilon. But in this picture, I want to think of this. I want to think of these inequalities vertically. Okay, that's why I'm drawing these. And I draw the heights. Okay. I fixed my epsilon. Okay, imagine these are perfectly horizontal. So it's a horizontal strip of side length 2 epsilon, if you want. I say, oh, if my input value, if my horizontal value is within a delta of x star, so maybe something like this. So x star minus delta, x star plus delta. Then any x, say here, any x within this vertical strip, when you apply f to it, is going to land to something, some point in this box. Okay? maybe it's going to land to this point. Okay. Yeah.
I have a little question for, so since it's for all epsilon, doesn't that basically imply that if there is, you know, if we can pick a delta, then our epsilon can just be some infinitely small number?
Well, I mean, okay. First imagine epsilon to be large. Your horizontal strip is very thick.
Yeah.
Okay? Then you don't need to control the vertical strip that much for continuity. Then you sort of start zeroing down on f of x star. So the thickness of the horizontal strip keeps shrinking and shrinking.
Yeah.
As you do this shrinking, you would like to be able to shrink the vertical strip also, so that you're always within this little box. So in this box, you want to think of sort of, you first figure out the length of this side. And once you have the length of this side, you would like to be able to engineer the length of this side. Does that kind of make sense?
Yeah, I think so.
Okay. Okay. Perhaps even before doing the proofs, then let's try to come up with a couple examples. F of x equals x. Well, of course, this should be continuous. Say continuous at x star, which is 0. It's continuous at any point, but let's just look at what is happening at the origin. Okay, so maybe I can draw it like so. Like this. So the diagonal is the graph of my function. Maybe let's look at x equals 1 actually, so that we can see it better. Okay. So my x star is 1, but of course my f of x star is also 1. Okay. Given an epsilon, positive, 1 plus epsilon, 1 minus epsilon. What's a delta that guarantees that the graph is going to be within this band? Well, in this case, for any epsilon, delta equals epsilon does the job. So delta equals epsilon. But in principle, if you wanted, you could have divided by 10, for instance. That would have worked too. Because this just says, for instance, instead of looking at 1 plus epsilon, 1 minus epsilon, just look at this little piece. The graph is completely within this horizontal strip. That's continuity. Okay. If I had something like this, however, say let's think. X sent to x if x is at most 1, and x plus 1 if x is greater than 1. It's a piecewise function. Okay. When you draw this, it looks like this. Like so. This is the graph of f now. Okay? It's clear that there's a discontinuity at 1. There's a jump. Okay? But let's try to figure out why f is not continuous using this. Well, if I were to choose epsilon to be 1/2, okay, so f of, and I'm looking at x star equals 1 again. Okay. Now my height again, because f of 1 is 1, my height is again 1 here. I take epsilon to be 1/2, so like so. But you see, no matter what delta I choose, I'm going to have to look at some numbers that are larger than 1. So it's going to go to the left and to the right. The left side is OK, but the right side, you see, under f, is always going to be outside this epsilon band. Okay? So you're not able to catch this piece of the graph of f within this epsilon, within this specific epsilon band. If epsilon was larger, that would be fine. But for sufficiently small epsilon, it fails. And that's why this function is not continuous at x star, you would say. Yeah?
Could you plug those values into that statement on the bottom? I don't have any visualizer.
So this would be 1/2. I said there's an epsilon such that for any delta, there's an x that is within a delta of x star, such that this is not less than 1/2. So I sort of take the negation of the statement because I was trying to show the discontinuity.
So like pragmatically, if you were trying to do this, you'd have to shrink it down as much as possible. Would you kind of like use the density of the rationals to find one like a little bit bigger always?
You can use that, yes. Yes, exactly. Yeah, so the 4 axioms / theorems about numbers, you're going to keep using these throughout the course. Yes, but that's true, exactly. In this case, it's not that important, or it's not really that required, because you would take a delta positive, and then you would take the average of x star, which is 1, and 1 plus delta. So given any delta, 1 plus delta over 2 is certainly at most delta away from 1. But the image is going to be not within 1/2. Yeah. OK. Well, I guess we don't have time to prove the equivalence of these two things. But I think it was good. We talked about certain intuitions and heuristics about continuity. We're going to continue on Monday. Thank you.